So we have talked about DFT. Now we add this STFT. Okay, so let's recap. Okay, you know this already. Now I just changed the number. Previously I use omega equal 2 pi f. Okay, and then this f, now I write this ugly symbol. But anyway, and then we no need to talk about this. And then again we can write this as inner product, right? And just a small note, we deal with complex number. So in inner product, two vector taking inner product for complex number, always do the complex conjugate. Okay, what's next? This is the thing I just told you, right? But this sigma thing now looks like this. Okay, it's the same thing. Okay, and then now here's the starting point of the new stuff. Why are we doing this STFT thing? If you look at this red thing, it says we do the whole thing from the entire time domain. This cannot tell when does frequency change occur. Suppose I have a signal that looks like very slow, okay, nothing, and then very fast. So that means low frequency, nothing, high frequency. I can also have high frequency, nothing, low frequency. Here's the drawback of DFT. If you do this whole vector and you inner product with the E, these two things give you the same spectrum, right? Because the spectrum tells you how many stuff are here. So this guy is equal to what? Equal to this thing, nothing, plus this thing, small thing, right? This is the same. We have high frequency thing, nothing, and then plus nothing, big frequency thing. Right? Frequency spectrum, what's the frequency spectrum? It's frequency. It didn't have any time information. So these two guys in the frequency world looks exactly the same. So there's no way for the frequency world to tell which is which. From time we can tell because this is low note and then suddenly high note. This is first high note and then suddenly low note. We can tell, but we cannot tell that. Then how do we distinguish them? Very simple. Instead of the full, we just do inner product with this part and then inner product with this part. That means we just take part, do it part by part. Then it will be what? It will be low, 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 high, high, high. This guy will be high, 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 low, low, low. Then they are different. So this is the idea of the ST. ST means short time. So you take not the full time, but a short time, and then you do this thing. So that means you do not take the full summation. And this is the idea. What's the difference here? Okay, now this is just fancy notation. What you do is you have a window. I will skip this detail, but let me explain to you how do we proceed. This is the high frequency and then nothing, and then this is. So what are you going to do? Very simple. In the first part, you just take, let's say my window is 2 boxes length. So that means my window looks like what? Nothing, 2 boxes, and then nothing. So what I'm going to do? I'm going to do a window, nothing. So this window, I call it window 1, will only extract this part. So that means these two multiplied together, I will get something like this, and then nothing, right? And then I will have a window 2, nothing, window 2. And then this guy multiply this thing will give me this part, right? So it will give me this part, okay? Nothing. And then I'm going to do the same thing. So basically it's like I take these 2 parts, and then 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 I take these 2 parts, and so on. So this whole process is like what? I shift this W, but it's also the same as I always keep my window like this, but I shift my whole signal, right? So for example, my first signal is this, but then I can also shift the whole thing 2 box here, then I have this, then I will get this 2 part, which is this 2 part, right? So this is the meaning of this. So what is this? Let's have a look. This is saying that I have a length L vector is my x, which the notation do not agree with each other, but the idea is I have a f here, the time series, but now I write x. And then what is this? The index is on n, okay, which is confusing, but anyway. So I just have a h is shift. They have a fancy name called hop size. And I just have different m, it will shift. And then I shift the whole thing, and then I multiply it with the same window. This never change, there's no m. And then I do the whole DFT. So that means what is STFT? It's the same as DFT, but now this guy, I will shift this thing and multiply with a window. And window is what? It's just 0 and 1. You can think of it as 0 and 1. So this is the idea. Do not be confused by the math. It's not important. You need to know the idea, the detail. So this is just math. So this is the idea. So this is my time domain thing. It's a length L vector. So this part is this part, right? And then this red part is this red part. Here's a funny part. I can overlap. You can decide whether or not they overlap or they do not overlap. Usually people do overlap, because you don't want to have a sudden sharp changes. Because if you do not do overlap, what happens if the changes occur in the middle point? And you don't know. But if you do the overlap, then both of them capture the change. You can tell. And then what I'm going to do next is basically repeat the same thing. I have a green, this will be my green, and then I have my yellow, this will be my yellow, and then lastly is just the black thing, which is my black thing. So this is a funny process. This whole thing, what's the whole thing here? This whole thing, length is L, because length start with letter L, so I use L. So what is this? I have 1, 2, 3, 4, 5. I have 5 things. Again, these two PDF use different notation, so they confuse each other. So, but that's not important. Make sure you understand the idea and the concept. Okay, and this process has a very fancy name called Henkelization, because this is called Henkel matrix. You don't need to know all the detail. Okay, you don't need to know detail here. Okay, so in other words, what you are doing, let's recap what we are doing in DFT. You have a frequency time domain signal called f. We do this. This is what we do previously in our no. This is for one particular frequency, right? And if we do the full thing, is we have f equal to what? W. This is w, okay, and then times f, okay, right? So if I now do the same thing, the notation is slightly different. So what I'm doing is that I now recall this w, this phi thing, okay? So basically, this is DFT, okay? This phi means frequency transform, okay? So this phi and this phi are the same thing. And then what I'm going to do, I have a window, right? So now I just insert a window inside. And what's window? Let me recall. You have a time signal like this, okay? Window is just a 0 or 1. So if my window is all 1, that means I take everybody here. Then this thing is just 1. It's the same as I didn't write, right? Because I can insert 1 here, right? But usually I will going to do is a window is just a finite thing. It's like, okay, I just take this part. So I'm going to do what? The first 2 boxes in this time domain, I will take everything. The rest, I don't care. So this is the meaning of the W. But then if I only write in this way, I only take this part. What about this part? What about this part? So I'm going to do is I shift this thing. Instead of here, I shift two position from here. Then I will have this thing. Then these 2 parts in the window, I will be getting this 2 parts. And then I shift again. Then I will get these 2 parts. And this shift operation, I write this funny arrow, meaning no shift, shift 1 time, shift 2 times until I shift m time. What's m? M depending on the hop size and how long is the whole thing. So this is the meaning. So therefore, what I do is I change from this notation, insert a w here, and repeat multiply f many times. So this looks like what? This is the full expression. I have my Fourier transform matrix, which is the DFT matrix. I have a window, which is just 0 and 1. And then this is shifting, right? I didn't change anything. And I write the arrow to represent how many times I shift. This means I do not shift. This means I shift 1 time. This means I shift 2 times, blah, 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 blah. And the shifting depends on the hop size. And then in the abstract sense, this ugly notation can be written as something called Henkelization, which is just fancy name. You don't need to know what the heck it is. Once you know how to implement it, you can do the opposite. So what's the opposite? Ignore the crazy math. Look at the picture. So basically it's this. Once you do the STFT, you have this is what you have for the STFT. You have a bunch of bars. So basically it's the opposite of this picture. Previously you have this black thing, give you rainbow. Now I give you rainbow, give me back black line. It's the same. So I have a rainbow. I just take this out and take this out, do the inverse matrix multiplication. These 2 parts are what? Overlap, right? Then I just take average or weighted sum. Then I will give me back the x. So that's it.